Swayam Prabha. Digital India. Educated India.
Hello everyone. So we will continue with the mechanical characteristics. At present we are discussing the tensile behavior of textile material. Now if we see the picture, it has got three different activities, and the story we can say tell it as a track and rope story. If we see the picture 1, where a track is tied with a palm tree and track is moving at a constant speed. So here we assume that track is moving at a constant speed, and this is a textile rope, and the movement of the track, and due to the load applied by the rope on the palm tree will bend it little bit, and palm tree will try to resist its bending because of its strength, and the amount of force applied on the palm tree will result the bending, and from that, if we know the characteristics, bending characteristics, we can measure the load applied on the rope. The picture 2 is again track and rope story, where the wall is there and the rope is tied with a hook in a wall, and the track, and here again track is moving at constant speed. That is our assumption. Track is moving at constant speed. And in third one, we try to keep the story same, track and rope here, but here the track is being filled by water at constant speed, constant rate we are filling, and here the load is being exerted by the track on the base. So these are the three stories. Now if you see this story here, story 2, the rope is getting extended at constant rate because the track is moving at constant speed. Here the other side of the rope is fixed on a stationary wall. The wall is not moving. So the rope will get extended at constant rate as the track is moving at constant speed. So that's why this process is known as, this type of loading is known as constant rate of extension. So the rope is extended at constant rate. And story 1 is that here story 1, here the track is moving at constant rate, but elongation is not constant because some portion of the elongation is actually consumed by the bending of the palm tree. So here in this case, although truck is moving constant speed, the extension is not at constant. So that's why we can term it as constant rate of traverse. So between the constant rate of elongation and constant rate of traverse, the difference is that in constant rate of elongation, one end which is represented by the wall is fixed, other end moves at constant rate. But in constant rate of traverse, both the ends are moving, but one end, which is the truck end, which moves at constant rate. So which moves means which traverses at constant rate. That's why this is called constant rate of traverse. So constant rate of elongation and constant rate of traverse, one should not get mixed up, it should not get confused. And as the truck is being filled by water at constant rate, so that's why the loading is here at constant rate. So it's called constant rate of loading. So we will find the situations, different situation in practical application where constant rate of elongation, constant rate of loading or constant rate of traverse takes place. And due to this constant rate of loading and constant rate of traverse or constant rate of elongation, the stress strain behavior changes. And if we see that if we use a particular material for say constant rate of elongation, we test it using constant rate of elongation, but its application will be there where constant rate of loading is applied. In that case, the result will be wrong as far as that particular application is concerned. So we can represent this in the other way also. Constant rate of elongation, as we have seen, one end is stationary, other end moves at constant rate, so moving jaw. So dx dt is at constant. That is the movement speed of this jaw is constant. So elongation rate is constant. And constant rate of loading, the movement of the jaw is not uniform, it's not constant rate, but it will move, it will extend in such a fashion which will maintain the constant rate of loading. So the force applied on the specimen, the rate will be constant. So at that same constant rate, the loading will be there. And constant rate of traverse is that where both the jaws are moving. So it doesn't follow the constant rate of elongation or constant rate of loading. So effectively there are three types of testing: constant rate of elongation, constant rate of loading and constant rate of traverse. It's called CRE, CRL and CRT. So CRE, rate of increase of specimen length is uniform. CRL's rate of increase of loading is uniform, and CRT, where the pulling one clamp at uniform rate, the load is applied through the other clamp. So in the story we have seen that when the truck is being pulled at constant rate, the other end will be applying the load, and that's why the, the palm tree is bending. So other end moves appreciably, which will actually be used to measure the load. Other examples are practical examples of when we fill a bucket at constant rate, water is being filled, so the loading on the rope will be at constant rate. And suppose an elevator on lift, the lift, a person, different students are entering into the lift, and if we assume the mass of or load of the weight of each student are exactly same, and if we assume they are entering into the lift one at a time at constant time intervals, like per second if one student is entering, in that case the loading on the rope will be at constant rate, so it will work as constant rate of loading. Now the problem is that our most of the universal tensile tester works on constant rate of elongation principle, and a rope which will be used for say lift, elevator, and if we test the particular rope in a CRE principle, but effectively it will be used for CRL application, then the result which we will be using, the strength result or load elongation behavior, will be misleading. Let us see why is it so. So two yarns, two portions, so this is same yarn, one is testing using CRE principle, another is CRL principle, and the shape of the load elongation curve for the time being we assume they are exactly same. Now when it's working at CRE principle, let us see, CRE means every second, so it is suppose up to 5 seconds we have seen, the extension at each second interval will be exactly same. Okay, but the loading you can see from the curve, in first second the loading will be maximum, and in the first 2 seconds, you can say next 1 second, the loading will be subsequently loading will be lower, sufficiently lower than the initial second, and for subsequent seconds we can see second to third it is very low, that means the extension is there but loading is not increasing. Third to fourth, again the extension will be there but loading is not increasing in that rate, but fourth to fifth the loading is again increasing. So due to this type of shape, so rate of elongation when we are keeping constant, the rate of loading is changing. Similarly, when we keep the CRL principle, that means the loading is increasing. So 1 to 2 second, the same loading, it is increasing at constant rate. In that case, if we see, the extension will be entirely different. For fast load, the extension is low, but second extension will be little bit higher. Third, it is further higher. Fourth, it's maximum. Third to fourth, it's maximum. Then it's again reducing. So depending on the nature, the extension is increasing. Now, looking at the earlier diagram, say let us see, this is the condition, the elevator. So in the lift, so load 1, so one student has entered, so it has extended little bit. Then 2 students have entered in the elevator, and it has extended little bit further. And when third person is entering, it has extended suddenly, extension will be there. And fourth person, it is so, because we have tested in CRE principle, we know this is the pattern, but the behavior will be entirely different when we actually encountered CRL type of situation. Okay, here it is explained, which we have discussed here. So if the specimen length increases in the CRE machine, the rate of loading will decrease subsequently. So we can see here, suppose specimen length, it is short specimen, and for the time being, if we eliminate the effect of gauge length, in that case, for short specimen, the breaking elongation will be low, but breaking load is constant for both the cases. We are eliminating the effect of the gauge length here, and for long specimen, the breaking elongation will be more. So if it is working in CRE principle, it's working. Suppose this is 1 second, 2, 3, 4, 5 second, 6, 7, 8, 9, 10. This is 5 second, 5 second, and this is 10 second. And breaking load is say L. That means for short specimen, the rate of loading will be L by 5. For long specimen, average rate of loading will be L by 10. That means this is the rate of loading. That means if we increase the gauge length, the rate of loading applied on the material will be lower if it works on CRE principle. That means shorter length if we take gauge length, that means in working in CRE principle, the rate of loading will be high. Now let us try to solve few numericals which will make our concept clear. So considering the breaking elongation and gauge length remains unchanged. So breaking elongation is not changing and gauge length we are not changing. If the rate of extension of yarn is tripled, we are in rate of extension we are increasing by 3 times. The percent increase in the measured yarn strength would be, so we know the standard relationship we have discussed. In first stage, breaking time is S. So gauge length remains same and breaking elongation also same. So breaking time is S, and when we increase the rate of extension to 3 times, that means breaking time will be S by 3. In second stage, breaking time T will be S by 3. So from standard relationship, you can see percent change in breaking strength is Ft minus Fs by Fs multiplied by 100, and this is given by the relationship 0.1 log multiplied by log S by T. Okay, and S by T, if we know S by T will be S by 3 will be 3. S by T is 3, so log 3 will be there, and if we solve this, it will be 4.77%. That means if we increase the rate of extension 3 times, we will get the higher strength of the material by 4.77%. Now similar numerical, if a yarn shows 60 centinewton strength when time to break is 10 seconds. If the rate of loading is increased to cause the yarn break at 1 second, then breaking load will be, so this is another time numerical, 10 second it's 600 centinewton, and we know the relationship, this is the relationship. So if 1 second, for 1 second breaking force will be, for 1 second of breaking time, so breaking force will be F1 equal to F10 multiplied 1.1 minus 0.1 log 1, for 1 second it will be 660 centimeter. Okay, so for 10 second it is given, so we have used direct relationship, so it is 616 centinewton. With 550 millimeter specimen length, the strain rate in percent per minute on tensile tester with 10 meter per minute jaw speed would be the jaw strain rate. So strain rate is equal to jaw speed by specimen length. So jaw speed by specimen length, so 10 by 10 is the jaw speed, specimen length is 0.55, so 550 millimeter, so 0.55 meter, so 1818.18%. that is the strain rate. Again similar numerical with 500 millimeter specimen length, the strain rate on a tensile tester with 5 meter per minute speed. The same way we can get, it's a 16.67% per second. This is percent. So this, if we take, it's a percent per minute and 1000% per minute, that will be 10 times, and per second it will be 16.67. Now again for time to break type of numerical, if a yarn shows a strength of 350 centinewton when the time to break was 10 seconds. If the rate of loading is increased to cause the yarn to break in 2 seconds, that means 5 times reduction, then the breaking load will be, here F10 is given 350 centinewton, so the 10, and here F1, so time to break for 2 seconds, so it's F1, so F10 1.1 minus 0.1 log 22 2 seconds, so we can directly get the value is 374.46. so for 2 seconds, initially it was, for 10 seconds it was 350, for 2 seconds it has become 374.47. so as 10 was assumed to be the standard time, or any other standard time we can also measure. Now this is a numerical where we would like to measure the effect of gauge length and effect of traverse speed. Now see here, a 40 NE 6733 polyester cotton blended yarn. So this is not going to be used because here we are not measuring the tenacity, only load value we will be measuring. So this yarn showed a breaking load of 300 gram force when tested in CRE tester with 150 gauge length and 150 traverse rate. So traverse rate, initial traverse rate is 150 per minute, millimeter per minute, and the gauge length was 150 millimeter. And what we are doing, what we want to percentage expected percent change in observed tenacity of yarn or load, breaking load of the yarn. If the traverse rate is increased to 3 times and the gauge length increased to 3 times, that is 450 millimeter and 450 millimeter per minute traverse rate. So when we increase the traverse rate, we are keeping the gauge length constant, and when we increase the gauge length, the traverse rate is kept constant. Okay. Assume a constant breaking extension, so always the breaking elongation is 25%, and single yarn strain CB is 10% for all the above conditions. These are the assumptions. Now let us try to do one by one. First, change in traverse rate. We are changing the traverse rate from 150 to millimeter per minute to 450 millimeter per minute. That is, the breaking time to break will be reduced by 3 times because our breaking load is constant. Breaking extension is constant. Three time reduction will be there. So time to break the yarn at 150 millimeter per minute is say S, and at 450 millimeter per minute it will be T. So S by T will be 3 times. 3 times increase in, so reduction in the time to break, S by T. So the relationship we have already discussed. Ft is the time required for 450 millimeter per minute speed, and Fs is for 150 millimeter per minute speed. So S by T equal to 3. So we can calculate that this is 3, S by T is 3, where log 3. So from there we can calculate it's a approximately 4.8% increase. If we increase the traverse speed from 150 millimeter per minute to 450 millimeter per minute. Now let us see how is it affecting the gauge length. So how the gauge length is getting affected, how the gauge length is affecting the strength from the following relationship. So this relationship we have already discussed, okay, where SRL is the strength at 450 millimeter gauge length, and SL is the strength at 150 millimeter gauge length. So R will become 450 by 150, it will become 3. So using this, and we know that we can calculate V if we know the CV%, where it's given CV% 10%. So V will be 10, already given. So R is 3, V is given as 10. So we can directly use this value, all this value, and to get the percentage change is 8.2%. So SL minus SRL by SL, this is 8.2%. Next, similar numerical. If the extension rate of extension of yarn is 4 times, then what will be the percentage change in the measured yarn strength for same gauge length, considering the breaking elongation constant. So similar numerical. So S by T will be 4. So second stage time to break T, first stage time to break S. So S by T will be, so T will be S by 4, and for this relationship, we know this relationship, Ft minus Fs by Fs equal to 0.1 log S by T, and if we multiply by 100, we will get the percentage change. So here if we solve, we will get the value 6.62, 6.02. 6.02. That means if we increase the rate of extension 4 times, we will get increase in observed yarn tenacity 6.02 times more than the existing. Next numerical. if a yarn shows a strength of 440 centinewton when the time taken to break 10 seconds, considering the breaking elongation remains unchanged, calculate the breaking load when the rate of loading increased to cause the yarn at break at 1 second. So 10 times increase in the rate. So here we'll see F1, so 10 so standard time 10 seconds it's given, so we can directly use this formula. That means rate of extension is increased, so standard time 10 seconds, so F10, so we can use this direct formula and we will get the value of the strength at 1 second. Time to break at 1 second, it will be 484 centinewton. So similar numerical here. A tensile tester works on CRE principle and rate of traverse is 3 millimeter per second. The breaking load of yarn is 500 centinewton at a gauge length of 100 millimeter. So what we have to calculate? Calculate the average rate of loading. So average rate of loading in centinewton per second when the gauge length is increased to 500 millimeter. So initially it is 10 millimeter, sorry 100 millimeter, and then we are increasing the gauge length to 500 millimeter. So we have already discussed, if we change the gauge length and the instrument works on CRE principle, with the increase in gauge length the rate of loading drops. That we have discussed. Now let us try to calculate. Assume a constant breaking elongation of 25% and single yarn strength CV is 50%. Okay, for all above condition. Now here the approaches will be different. Earlier example, while discussing, we have discussed that with the change in gauge length, we have assumed that breaking strength is not changing. Still there was a reduction in rate of loading. But here what we are doing, we are changing the gauge length, so we will calculate the impact of the breaking load first. So at 100 millimeter gauge length, the total extension, breaking extension is 25% given. The total breaking extension is 25 millimeter. So time to break of yarn total extension by rate of extension. Rate of extension is 3. So it will become 8.33 seconds. That is the time to break. So the average rate of loading is breaking load by time to break. That is, breaking load is 500 centinewton by time to break is 8.33. So it will be 60.02 centinewton per second. That is the time to average rate of loading. So we will be calculating average rate of loading. Rate of loading changes always depending on the type of and shape of card. But here we are assuming from the beginning to the end point, what is the average rate of loading. Now coming to the second stage, at 500 millimeter gauge length, total extension will be 125 millimeter. So 25% extension earlier case we have assumed 25% breaking elongation, and time required to break the yarn, total extension by rate of extension, so 41.67. Okay, that is the time. Time to break. Now we have to calculate the breaking load at gauge length 500. So initially the gauge length was 100 mm, 100 millimeter. So breaking load is 5 times. So R equal to 5. CV percent given 15. So V 15. So in this equation, if we replace these values, so we will get SRL by SL. That means at 500 millimeter gauge length, the breaking load will be 0.826 times of the breaking load at 100 millimeter gauge length. That means this SRL by SL will be 0.826. That is, it will be reduced. So the breaking load at 100 centimeter gauge length was 50 centinewton, and breaking load will be 413 at 500 millimeter. So 413, and 413 breaking load will reach after 41.67 seconds. So we can calculate the average loading, rate of loading, that will become 9.91 centinewton per second. So at 100 millimeter gauge length, the breaking load was 60.02 centinewton per second, but when we increase the gauge length to 500 millimeter, this has dropped to 9.91 centinewton per second. That means if when we are increasing, the material is being loaded at lower rate. Next one, 32 text cotton yarn results a breaking load of 450 centinewton when tested in CRE tester with 100 millimeter gauge length and 100 millimeter traverse. Keeping the gauge length constant and assuming the constant breaking extension of 30% for all the above condition, if the traverse rate is increased to 500, same numerical. So 100 millimeter per minute to 500 millimeter per minute. So we are not going to discuss in detail. So that means S by T will become 5. So it will be, there will be 6.99 times percent increase in the observed yarn tenacity. And that means which means that 450 centinewton was there. So this will become 400 sorry, this is it will become 478.659. So observed tenacity will be, or strength will be 478.65. Next is that the breaking strength of a cotton is 77.5 Newton. Now here twist per meter is given 765 twist per meter, and twist multiplier is giving 4, which is in your indirect system. Now we have to calculate the tenacity. So tenacity means is breaking load, which is 7.5 Newton or 750 centinewton, divided by the takes of lift. And we know TPI equal to TM under root count. So English count will be TPI by TM square. So using this relationship, we can calculate the yarn linear density from twist per unit length and twist multiplier. So first we have got here twist per unit length in twist TPM, twist per meter. So we can convert it to twist per inch, and then we calculate first English count, then we convert it to text. So this conversion we have already discussed, we are not going to discuss here again. So TPM is 765, TPI twist per inch will be 19.43. Just conversion, TM is given, so any is, you can calculate any English count is 23.597. So TPI TM unto any, so any will be TPI by TM square. So if we use this, we will get this value 23.597, and takes of the yarn will become, so 590.59, 590.5. So this equal to 590.5 divided by 23.597 equal to 25.02. So this we are getting text value, and we can calculate the tenacity, so which is 29.97 centinewton per text. Now we will quickly discuss the methods of measurement, and this we will do in the next class. Thank you.